The world froze. 100 feet above the twisting canyon road, the 1978 Honda CB750 roared one moment, then choked on its own breath the next. Zara, a master restoration mechanic, felt the loss of power instantly. The engine, her masterpiece of polished aluminum and steel, had just died. Not stalled, died. No spark, no compression, no cycle. The four-stroke heartbeat, intake, compression, power, exhaust, had flatlined. What was supposed to be a joyous test ride had become a terrifying 60-second physics problem. Her life, and the life of her cherished machine, was now just a function of gravity and friction. She had to fix this, right here, right now.
The silence after the mechanical scream was deafening. Zara ran a hand over the cool metal of the engine block. The CB750's engine, an inline-4 configuration, a true legend, is the epitome of the four-stroke principle. Each cylinder operates on a cycle, a perfect synchronized ballet of components designed to convert the potential energy of gasoline into the kinetic energy of motion. Zara quickly traced the failure. The ignition was fine. Fuel flow was strong. It had to be the mechanical timing. She pulled a small inspection cover. As she slowly kicked the starter lever, she watched a small internal timing gear spin. It was moving, but something felt off. A quick measurement with a precision caliber confirmed her fear. The tiny, almost microscopic woodruff key, a small semicircular piece of metal that locks the cam gear to the camshaft, was missing, or more accurately, sheared. The camshaft, responsible for opening and closing the intake and exhaust valves, was now spinning freely, completely decoupled from the crankshaft. The engine was alive, but its lungs and voice were silent.
A four-stroke engine works because of perfect, synchronized timing. Let's look at what the sheared key destroyed. 1. Intake stroke. Suck. The piston moves downward, increasing the volume inside the cylinder. The intake valve is precisely timed to open. The resulting vacuum pulls in the air-fuel mixture. The breakdown? With the camshaft spinning randomly, the intake valve might be closed when the piston moves down. Result: no fuel-air mixture enters. The cylinder is starved. 2. Compression stroke. Squeeze. The intake and exhaust valves are both closed. The compression seal. The piston moves upward, compressing the mixture into the small space of the combustion chamber. This high-pressure, high-temperature mixture is ready for ignition. The breakdown? If the intake or exhaust valve is randomly open due to the untimed cam, the piston just pushes the air-fuel mixture right back out. Result: zero compression, which means zero potential energy for the next step. 3. Power stroke. Bang! The spark plug fires at the precise moment of maximum compression, TDC. The explosion forces the piston violently downward. This is the only stroke that generates power, transferring force via the connecting rod to the crankshaft. The breakdown? Since there was no compression and no fuel-air mixture, steps 1 and 2 failed, there is no bang. The spark fires into an empty, dead cylinder. 4. Exhaust stroke. Blow. The piston moves upward again. The exhaust valve is precisely timed to open. The burned gases are pushed out of the cylinder, preparing for the next intake stroke. The breakdown? The exhaust valve may be closed when the piston moves up, causing the burned gases to stay trapped, creating back pressure and preventing the next cycle from starting.
Zara realized the shearing of a single, inexpensive key had thrown the entire thermodynamic loop into chaos. The engine couldn't breathe, squeeze, fire, or exhale. A good mechanic never travels without the essentials. Zara didn't have a new woodruff key, but she had a solution often used in a pinch: cold welding and precision shimming. Step 1. Locating true top dead center, TDC. She first needed to find the engine's 0 point. This is top dead center for the number 1 piston, the highest point it reaches in the cylinder bore. She carefully rotated the crankshaft until the timing mark on the flywheel aligned perfectly with the engine casing. This ensures the piston is where it needs to be for the start of the power stroke. Step 2. Valve overlap and the camshaft reset. Now she had to align the camshaft. The camshaft position is critical. When the number 1 piston is at TDC on the power stroke, the camshaft must be in the position where both the intake and exhaust valves are perfectly closed. This is the compression phase. She manually rotated the camshaft until the alignment mark on the cam gear lined up with the pointer on the cylinder head. This is the key moment, the exact point of valve overlap, the tiny window where the exhaust valve is closing and the intake valve is beginning to open, signaling the transition from exhaust to intake. Step 3. The improvised lock. The original hole for the sheared woodruff key was now a mangled mess. She couldn't use a simple key. Zara took a tiny piece of hardened steel shim stock from her kit and carefully tapped it into the original keyway space on the crankshaft, creating a wedge. She then aligned the camshaft gear onto this new wedge and secured it with the original bolt, torquing it down with a micro wrench until it was impossibly tight. The mechanical principle: she wasn't relying on the wedge alone. She was relying on friction torque. The high clamping force of the bolt creates enough friction between the camshaft gear and the crankshaft to prevent slippage. The shim is a secondary safety measure. The torque value for this particular engine is 35 foot-pounds. Her wrench was small, but she had an excellent feel for the rotation. This was the moment of truth. An engine is a pump. It must create a perfect seal to work. If her timing was off by even a single degree, the engine would be crippled, or worse, destroy its internal components. The 4-stroke cycle demands precision. Zara adjusted the choke and hit the starter button. First turn, a hesitant whir. Nothing. Second turn, a cough, a puff of white smoke from the exhaust, a sign of life. The air-fuel mixture had ignited momentarily. Third turn, vroom! The 4 cylinders roared to life, settling into a low, rumbling idle, the beautiful, balanced hum of the perfectly timed inline 4. The moment the engine fired, the mechanical ballet was complete. Intake was sucking air and fuel in. Compression was squeezing it tight. Power was converting that squeeze into a downward push on the piston. Exhaust was clearing the path for the next cycle. The potential energy of the gasoline was once again being transformed into the kinetic energy of the spinning wheel.
The 4-stroke engine isn't just a machine. It's a living testament to physics. It's a closed-loop system where failure in one step, the timing, the fuel, the compression, guarantees failure in all. In the real world, the 4-stroke cycle is the invisible rhythm of our daily commute, our travel, and our power tools. Zara's story shows that a seemingly catastrophic breakdown was simply a momentary loss of timing. By understanding the intake, compression, power, exhaust flow, and knowing the critical role of timing, she didn't just fix a bike. She reestablished the perfect, rhythmic flow of energy conversion that defines all modern internal combustion. Every time you hear an engine purr, remember the complex dance of the valves and pistons, a mechanical heartbeat, ensuring that one small explosion can carry you 1,000 miles.